Welcome everyone back to 264A Automated Reasoning. Today we will be talking about an exciting and current topic, which is explaining the decisions of machine learning systems, in particular classifiers. This is yet another application of logical reasoning and tractable circuits. In fact, the approach that we will be discussing today is more general. It's not just for explaining decisions, but can be used more broadly to reason about the behavior of machine learning systems. In fact, towards the end of today's lecture, we will also talk about robustness, not just explaining decisions, but measuring how robust these decisions are. These are all very current topics, and they became important as we started deploying systems and people wanted to know why are the systems doing what they're doing. So we will find ourselves actually using techniques that we looked at before, in particular what we did last time when we discussed prime implicants and when we discussed model-based diagnosis. Even though these were actually relatively old techniques, we'll find that actually they became now in the forefront as far as playing a role in these applications. So let's go to the whiteboard and start our discussion. All right, so let me first start by the big picture here to let you know what we're going to be doing and what is really the basic idea underlying this connection between machine learning systems and logical reasoning. So as you may know, a lot of what's happening today in AI is actually based on what we would call machine learning systems, and there tend to be classifiers, meaning they take an instance and they render a decision on it. And these classifiers can take various forms. So they could be Bayesian network classifiers, neural network classifiers, or random forest. These are very well-known type of classifiers. And they're learned. They're learned from data, in this case, labeled data, in which you have input, output, and then you learn a classifier that kind of try to imitate and learn this association between the output and a particular input. Now, the main observation underlying the approaches that we will be talking about is the following: that even though these systems are numeric, and even though they learn from data, they typically represent discrete functions in the sense that the input instance is a discrete creature and the output is a discrete creature, typically a decision yes, no. So what we would like to do is capture that input-output behavior using a tractable circuit. So in a sense, we will take the machine learning system and compile it into a tractable circuit that has the same input-output behavior. Because if this is discrete and that's discrete, then what's happening inside, in a sense, is irrelevant. The fact that it's being numeric, it's just a sophisticated way of specifying a discrete function, all right? So we can get that in the form of a tractable circuit. And once we do that, then we can do all kinds of things. And here are example questions that people are interested in today. And in fact, we will talk pretty much about each one of these as we go on. So let me give you a concrete example so that you see this a little bit more vividly. This is an example of a machine learning classifier. It's one of the simplest you can encounter. It's known as a naive Bayes classifier. It's a special case of what people call Bayesian network classifiers. So what you have here is what we call features: urine test, blood test, scanning test, and we have what we call the class variable, pregnancy. And the idea is I'm going to give you a patient and I tell you what happened to their test results, and I want you to classify them as pregnant or not. And in these classifiers, you can see these numbers. These represent the false positive and negative rates of these tests. You have something called the class prior. And the idea in this case is once you give me the values of these, I will go compute the probability over pregnancy, posterior probability, and then I check against the threshold. In this case, it's 90%. And if that probability is greater than or equal the threshold, I will say this person is pregnant. Otherwise, they're not pregnant. All right. So the interesting thing here is these are typically learned from data, these numbers. But then to render a classification, to render a decision, you have to do probabilistic inference. Well, interestingly enough, the input-output of this classifier are discrete, because if you look at the features, U, B, and S, in this case, they're even binary, true, false, and the output is a yes-no decision. So this whole box, even though it's numeric and even though it's learned from data, is just a sophisticated way of learning a discrete function and specifying a discrete function. So if I'm interested in the relationship between the inputs and the output, I don't need numbers. I can specify this symbolically. And in fact, in this particular case, this exact classifier can be represented, for example, using an OBDD, a decision diagram. We've gone over these representations. This is the notation that is used typically, but we've seen how these are actually nothing but an instance of negation normal form circuits with certain properties. Now, in what sense is this a representation or this decision graph a compilation of the naive Bayes classifier in the following sense? If you give me an instance, let's say this one, someone tested positive, negative, negative, you can classify it according to this guy by following edges as we have discussed, right? So urine is positive, I go this way. Blood is negative, I go this way. Scanning is negative, I go this way. So the decision is no, this is not pregnant. Now, if you go and try to compute the posterior on pregnancy, given this instance, and check against the threshold, you will get the exact same decision as in here. In fact, there is a compilation process that takes you from this to that, which guarantees that the two systems will have the exact same decisions on every possible instance. And that's what we mean by basically capturing the input-output behavior of the machine learning system. Now, today, we will not talk about the compilation process of how do you take something like this and compile it into a symbolic representation that captures its input-output behavior. That will come later. Today, we'll talk about what are we going to do with these things if we have them. So more generally, the big picture here is what else can I compile beyond naive Bayes classifiers? What do I compile them into? It doesn't have to be an OBDD. Right? It could be some other tractable circuit, and which one is appropriate depends on what you want to do, what kind of questions you want to ask about the system. And today we'll look at the last question, what can you do with these symbolic representations, focusing mostly on explaining decisions and a little bit about robustness towards the end. So this story will be continued later, particularly with respect to the compilation. Now, interestingly enough, this idea of taking a machine learning system and compiling its input-output behavior symbolically is pretty old, actually. We proposed this in 2003. Hei Chan, one of our previous PhD students, actually came up with a compilation algorithm from naive Bayes to order decision diagrams. Things were different in AI then. Barely anybody paid attention to this at that point. But now that we started deploying systems, these kind of questions became relevant. In fact, the title of that paper was Reasoning About Naive Bayes Classifiers. More recently, we extended this to a more general naive Bayesian network classifiers to tree structures and general BN classifiers. Again, this was the work of another student of us, Andy Shih. He was actually a master's student at that point. And now he's a PhD student at Stanford. So we'll talk about this later, but I just want to make a couple of observations before we move on. So when you compile these machine learning classifiers into symbolic representation, you see something interesting. Here's some of the examples that were compiled. These are Bayesian network classifiers from the literature. This has to do with assessing skill level. These represent different skill levels, and you've got your features and you're trying to actually map the input from this to that. So in this case, you would compile this into 3 different classifiers, because if you're assessing the skill, that would be one classifier, this another classifier, a third. And here's another example from diagnosing problems when printing. I think this was built by Microsoft Research a while back. This is another example classifier for breast cancer from mammography reports. This, I think, came from Stanford Medical Informatics. And one of the observations is when you compile these into symbolic representations, the size of these symbolic representations vary. And sometimes they're pretty simple and sometimes they're pretty complex. So this particular one was compiled into an OBDD that had only 156 nodes. And in fact, you're seeing it all on the screen without the labels. And this is for a particular ordering. You know by now that if you the size of this will be different depending on what total variable ordering you use when you do the compilation. But interestingly enough, this guide turned out to have relatively simple logic. But in some other cases, the sizes were pretty large and sometimes in the millions. And that was also sensitive to the threshold that you use. The point is, in a sense, when you do this compilation and you look at these circuit sizes, you may get a sense of how complex is the logic that's underlying these systems. But the other point that I want to make is that sometimes when people look at decision trees or decision graphs, because that's a native representation also of machine learning systems, right? You can learn a decision tree or a random forest. Now, decision trees are usually favored because people view them as intuitive. And you can look at them and see what are they doing compared, for example, to a neural network. And then when you see something like this and you say, oh, you're giving me a decision graph that has millions of nodes, how is that useful? Well, the point here is that we are not going to visually inspect these guys and try to make sense of what they're doing. We're going to operate on them algorithmically, as you will see later. So their size really doesn't matter as long as you're able to store the circuit. All right, so if you manage to compile it successfully and store it, in a sense, you are actually in good shape. And we will show you examples of that as we go on. All right, so what I'd like to do is, before we delve into the subject and talk about how do we explain decisions, I want to go over some preliminaries. I want to be clear on what we mean by classifiers, and particularly Boolean classifiers, because we're going to be focusing on them. I need to explain the notion of a monotone classifier, because that's relevant. And I want to review the minimum cardinality operations on circuits, because again, this is something that we will be using today. So let's go over classifiers and Boolean classifiers in particular. And please pay attention to this because we're going to be using these terminologies quite often as we go on. So in general, a classifier is just a function that you give it inputs and generate an output. A Boolean classifier in particular is a Boolean function. So it's a function that has the following form. It's over some variables. And these variables are called the features. And in this case, we're going to assume that they're either true or false. And therefore, the decision is 0 or 1, yes or no. What we're going to be talking about can be generalized to discrete classifiers, where these are discrete variables and the output is discrete, but we'll keep it simple and just focus on Boolean classifiers. Now, there is the notion of an instance. Everything we're going to be talking about now we've seen, but when you start talking about classifiers, there different terms are used. So the notion of an instance is a variable instantiation. So if you come and tell me x1 is 0, x2 is 1, xn is 0, we call that an instance, all right? Because this is now something that we're trying to classify. You plug that instance into this function, you're going to get either a 0 or 1, and that we call a decision. So the classifier has made a decision on that particular instance or classification. Right? And then we tend to distinguish between what we call positive instances or decision. This is when you evaluate the function on an instance and you get a 1. We say the classifier made a positive decision on the instance, and this instance is positive. And similarly, we have the notion of a negative instance and a negative decision. This is a negative decision, and then the instance in that case would be a negative instance. Sometimes we will have to distinguish between the notion of a feature and a characteristic. And these are used loosely in the literature, but in some of the papers I'm going to show you later, no, that distinction is made clear. So what's the difference between a feature and a characteristic? The variables on which the classifier acts, we're going to call them features. So these are variables. When a variable takes a particular value, we call it a characteristic, right? So in a sense, when we talked about this instance and the fact that x1 is 0 in that instance, we would say this is a characteristic of feature x1, all right? Sometimes we'll end up mixing them, but a characteristic is a specific value of feature. And therefore, sometimes we say that the instance is just a collection of characteristics. I hope this is clear. The other thing I want to stress here is the use of Boolean formula to represent Boolean classifiers. You've seen in this course, we've been switching between more engineering notation of talking about Boolean functions and more AI notation and talking about Boolean formula, and they're the same. So when we're actually manipulating things, we'll typically be using propositional formulas to represent classifier. Here's an example of propositional formula. Delta equals X or Y. So we have two variables, X and Y, and these are two features. So you can think of this classifier as over two features. Now, what happens here is you can think of delta as characterizing the positive instances, those that satisfy the formula. In fact, in our terminology, we call these worlds, right? Because worlds are full variable instantiations. Those are instances. So worlds that satisfy the formula are basically the positive instances. And in this case, we have three of them: X true, Y true, X true, Y false, X false, Y true. We have three positive instances. And then negative instances are characterized by the negation of that formula. So those worlds that satisfy the negation of the formula, those are the negative instances. And in this case, there's only one of them, which is X false and Y false. Now, this becomes somewhat important because some of the manipulations that we were going to be doing later, like computing certain type of explanations, will say, oh, I can do it easily if my formula is in DNNF form, is represented as a tractable circuit. Now, in general, if you want to reason about both positive and negative decisions, and therefore positive and negative instances, not only do you need to have that delta in DNNF, you also need its negation in DNNF, okay? So this will come up later. So typically you'll end up needing a representation of the formula and a representation of the negation of that formula in the particular form, because depending on whether you're reasoning about a positive decision or a negative decision, you'll end up working either with delta or with the negation of delta, okay? All right, we have one more thing to review, and then we will be able to show you the first kind of explanations that we will be working with. Now, the next thing that we want to review is, actually there's two more things. The notion of a monotone classifier. And this classifier is characterized as follows. If you have a positive instance, it will remain positive if we flip some of the negative characteristic and make them positive. Let's take a concrete example. Let's say we have a classifier over 4 features, and this happens to be one of these instances. So the first feature is positive, the second is negative, negative, positive. And the fact that it's a positive instance, what does that mean? That means the classifier is classifying it positively, is making a positive decision on it. Now, if this happens to be a monotone classifier, that means if you flip any of these negative features to positive, then the decision would remain positive. So in this case, I flip the first one to positive. In the second case, I flip this guy to positive. And in this case, I flip them both to positive. Those all should be positive instances. The decision would remain the same. And this is known as a monotone classifier. As an implication of this, you get the opposite. That is, if the decision was negative, then if you go and turn some of the positive features to negative, the decision remains to be negative. Okay, where does this come up? Just to give you an example, there is an interest, of course, of this, and this is an example of a property, right? Sometimes in certain domains and certain applications, you would want the classifier to be monotone. And I'll give you an example next. Here's an example from educational testing. And let's say this classifier is taking answers and whether and based on that, you want to decide whether to pass a person or not. And let's say in this case, Susan's correct answers include Jack's correct answer. So there's 50 questions, and Jack answered 40 of them. And Susan answered those 40 plus 3 more, right? Well, you would want the classifier to pass Susan if it already passed Jack, right? So it said that Jack is competent based on these 40 answers. Well, Susan did the exact same 40 plus 3 more, you would want it to be passed as well. That's an example of monotonicity. And one of the interesting things is if you learn a classifier from data, how do you know that it's actually monotone? These algorithms typically do not actually guarantee that. So that's something that is an example of what we would call properties of classifiers that we want to ensure, or at least verify. So if you cannot ensure it and you learn something, can you go and tell me, is it indeed monotone? Which is not easy if the classifier is represented numerically, but we'll see later that if you capture its input-output behavior using a tractable circuit, in some cases, this can be an easy question to decide. Now, we're going to use this twice. Once in the first type of explanations we're going to look at, they're geared towards monotone classifiers, and later when we do verification. Okay, the last thing we need to review before we move on, the notion of minimum cardinality. Remember, we discussed this twice before. You have a Boolean formula, you have models of that Boolean formula, and we define the cardinality of a model. In this case, we're going to define it as how many variables are false in that model. So in this case, this guy has cardinality 1, this guy has cardinality 3 because there are 3 false variables. And in this case, the minimum cardinality is the smallest cardinality attained by any of the models. In this case would be 1, assuming nothing below there is 0. Now, in this case, we define cardinality to be the number of variables that are false. You could have defined it the other way, which is the number of variables that are true. And the main thing we said about minimum cardinality is that you can compute this minimum cardinality easily if the Boolean formula represented in a particular form as a tractable circuit. And you can also do what we call minimization. That is, I want those models that have minimum cardinality. Can you get them? So let's just quickly show that. If your formula is represented as a DNNF, you can do minimum cardinality computations easily. Remember, in this case, we're using this particular definition of cardinality being the number of variables that are false. So you go to the leaves, and negative literals get the value 1, positive literals get the value 0. The boundary case is that true gets the value 0 and false get the value infinity, and you just walk through the circuit. And in that particular case, you just minimize at OR gates and sum at AND gates, and then here you get the number 1, which tells you there is no model for this formula that has cardinality 0. Every model has a cardinality 1 or more. And then if I tell you, fine, can you modify the circuit so that you can throw out everything that has a cardinality greater than 1? I just need those guys that have cardinality 1. We, in that case, showed that what you need to do is simply prune some of the edges in the circuit. In particular, we talked about the fact that you go to OR gates, and for every OR gate, any child that has a higher cardinality than that assigned to the gate gets pruned. So in this case, this guy has the OR, this child has cardinality 0, this guy has cardinality 2, we kill this guy. And similarly for that. So if we remove these edges, then we get the circuit, which is now guaranteed to only capture those minimum cardinality models. And in fact, if we remove the nodes that are no longer referenced, like this guy and that guy, it looks like this, okay? And now every model for this circuit has a cardinality of 1. Remember, this was still on DNNF, but for the minimization step, you needed smoothness as well for this to work. Okay, this circuit, as we mentioned before, represents the odd parity function. So a variable instantiation is a model of this if the model has an odd number of variables set to false. So there are 4 variables, that means 8 models. Those in which a single variable is set to false there's 4 of them. And then there's another 4 in which 3 variables are set to false. So in both cases, we have an odd number of variables set to false. So once you minimized, we got the circuit. And here's how we can enumerate the models of this by looking at subcircuits, which we did before. Remember, a subcircuit is you start at the top. For every OR node, you pick exactly one child. For every AND node, you pick all children. And if you do this, you end up getting a subcircuit that represents a model of the circuit. And this guy here is one of them. You can see exactly one variable is set to false. Here's another, exactly one variable set to false. Here's another, and this is the last one. So what this minimization step has done is excluded all of these 4 models in which 3 variables are set to false. All right, guys. So we're ready to move on. And when we talk about explaining decisions, we will end up looking at 2 types of explanations. The first one we'll start with is geared towards monotone classifiers. And the second one is more general. The first one is called MC explanations. And you want to guess what MC stands for? Given all of the review we did and just the review we did, it's called the minimum cardinality explanations. Now, what these guys try to do is the following. Let's say you get a yes decision, right? You have a yes decision. And the idea is that in these monotone classifiers, you want to think that the positive features are pushing to a yes decision. So I have a whole bunch of positive and negative features, and I'm trying to think which one of the positive features are really responsible for this decision. We'll take a concrete example shortly. So if you had, let's say, 20 features and 13 were positive, and you made a positive decision, do I really need all these 13 features? I need actually the smallest number of them that is responsible for this decision. And similarly, if the decision was negative, did I really need all of these negative features? I need the subset of them or the smallest subset of them that is responsible for the decision. The other type of explanations are called PI explanations. We'll talk about these later. So let's get started with MC explanations or minimum cardinality explanations. And we're going to show this first concretely by example, and then we'll show you how to compute them. But first, let's understand what is a minimum cardinality explanation. So what you have here is a classifier over 4 features. This is trying to decide whether to admit someone to a program. And we have 4 features: work experience, whether they're a first-time applicant, did they pass the entrance exam, have they met the university expected GPA, all right, these variables. Now, if you look at these variables or features, they're binary, yes, no. So in principle, I have really a total of 16 possible instances. And this is the decisions that are made by this classifier. So we're using bold X here to represent an instantiation of these variables. And you can see the decisions positive, negative. And let's look at the MC explanations. Okay, so here's, in this table, list them all for every decision. Let's pick the first one. This is an instance. And because the decision is negative, we say that it's a negative instance. And the question is, did I really need all of these negative features to reach this negative decision? And the answer here is no. The answer here is no. 2 negative features suffice. And there are various combinations of negative features that will do, and they're listed all here. Now, how do we get this? That's another story. We're going to get to this later. But look, the first and 2 being negative is sufficient to actually render a negative decision. These could have been positive, the 3rd and 4th. Also, the 1st and 3rd being negative is enough. ... There is various combination. Now, what does this tell you also? This tells you you cannot reach a negative decision using a single negative feature. There is only one feature negative and the others are positive. That's not going to happen. The decision will not be negative in that case. You need at least 2 negative features, and here's are all combinations of negative features that actually will render a negative decision. Let's look at the last one. This instance, everything was positive, another extreme case, and the decision was positive. So there's only a single MC explanation in this case. And what does this mean? This means you did not need 4 positive features. 2 are sufficient, 2 will do it. And the first and the last, no other combination of 2 positive features will do it. And this also tells you you cannot get a positive decision using a single positive feature, because if that was possible, you would not see this. You will see, sorry, If you could get a positive decision with a single positive feature, you will see this here, and this will not be the case. So by looking at this, you know two things. First, you need at least two positive features, and in fact, it happens to be exactly these two. You don't have other choices. Here we had so many choices, and so on. Okay, so we would say in this case, we have only one minimum cardinality explanation. It happens to be this one. Okay, let's take a concrete example or something a little bit more intuitive before we talk about how you compute these. Here's the classifier we looked at before. And in this classifier, I have an instance. And let's say it's Susan, and she tested positive for scanning blood and urine. Everything came out positive, and here they are. Now, if you look at this classifier and say, what do you think? And then it will come back and saying, Susan is actually pregnant, because you can see we followed the logic here, a decision diagram, and we reach a yes decision. And you say, why did you conclude that Susan is pregnant? And the MC explanation in this case comes back, says, because the scanning test came out positive. So even though I had all features being positive, this type of explanation is saying the culprit why you made that decision is that the scanning test was positive. You didn't need the other two positive tests. If we look officially at the definition, and here I did the same thing, we have 3 features and 8 instances, and this is the instance we were looking at. Everything came positive. The MC explanation is this. You don't need this to be positive. You don't need this to be positive. You only need that to be positive. And then you will make the same decision. Now, again, this is saying more. This is saying, yes, I can do it with one positive feature. I don't need this, but no other feature on its own will trigger this decision. So if you had blood test alone, that would not do it. If you had urine test positive alone, that would not do it. Only scanning test alone can actually give you that decision. All right, and let's take another more involved example. So same classifier, the instance is everything is negative in this case, okay? And you go and check the classifier and says not pregnant. And you say, why did you conclude that Sally is not pregnant? And the answer you get now is because the scanning test was negative and one of the blood and urine tests came out negative. What does that mean? They're all negative, but I don't need them all to be negative. I would have made the same decision as long as scanning is negative and one of these two. And now let's see in the official definition. This is again the full table showing you all MC explanations for every instance. This is the instance we're looking at. The decision is no, and you have 2 MC explanations, all right? One of them says scanning negative and blood negative. The other says scanning negative and urine negative. Either of these will do it. You will make the same decision. You did not need to have both of these are negative. Now, you have to realize how interesting this is, because this guy came from a machine learning system, from a classifier where there's all of these numbers that are learned from data and all of this probabilistic reasoning that is used to render decisions. And now I can make these qualitative conclusions and reasoning about it without invoking any numerical computations. The only thing I had to do is compile successfully its input-output behavior, and then you'll see how more you can do with this. And again, what we're doing here is basically geared towards features being positive and negative. And in a sense, this is more useful when the classifier is monotone. And when we're going to go to the next kind of explanations, we'll see that it's more general than this. Doesn't require a property of the classifier, and it will work easily with discrete features, not just positive and negative. But let's just see how we can compute these, because now we showed you what the definition is. And it turns out that these MC explanations can be computed in linear time, assuming your classifier is represented as a DNNF. And I have the star here to mean that you need the Boolean formula and its negation to be as DNNF. And I think someone mentioned earlier when I made this remark about needing both delta and not delta to be represented in that form, someone made a remark that OBDDs will be good for that because I can easily negate an OBDD correct. But what I'm going to show you next only needs DNNF. But yes, when you have an OBDD, then you can negate it easily. You cannot do this with DNNF. So let's go ahead and show you how this works. And before I move on, let me just mention, while MC explanations can be computed in linear time on circuit types like DNNF and OBDDs. The other type of explanations we're going to get to later, which is in a sense a more general, no, you cannot do it in linear time. The situation there is a little bit more involved, and we're going to get to this. So in a sense, while MC explanations are somewhat restricted in terms of their applicability, we can compute them more efficiently. Now, here's how we're going to do it. Let me show you, and you know this, by the way. The thing I'm going to mention now about how to compute them is something that we already know and we reviewed earlier. I'm talking about this guy. I'm talking about the same classifier, this guy, okay? And I'm gonna try to explain a positive decision. So I need the OBDD for the positive decisions. And what I did here is I converted it into a DNF circuit. We know how to do that, right? And I have this instance. And the fact that it's positive, it means the OBDD said, yes, this person is pregnant. So urine is positive, blood is negative, and scanning is positive. And as you can see, I have two positive features in this case. And the question is, if I want to compute the MC explanation, it's really asking, did you really need both of these to be positive? That's what we're trying to do. Can you flip some of these to negative and maintain the decision? And I want you to flip as many of them as you can. And it turns out to be a simple exercise in doing minimum cardinality, with one exception. The first thing I want to do is I want to say, okay, I'm trying to see if I can flip some of these guys to negative, but this stays negative. So the first thing I'm going to do is I'm going to condition this on B negative. All right, so we know how to do this, right? We can do this easily by simply replacing these guys into false and true, because this is negative. This becomes false, this becomes true. Now, what do I get? I get a Boolean formula or circuit over the variables U and S, okay? And it could be satisfied in different ways, but I'm only interested in those instantiations of U and S that have a minimum cardinality, meaning they minimize the positive literals. So in this particular case, we are doing, sorry, let me go back. We are defining cardinality differently. The cardinality of a model is the number of variables it sets to true. And I wanna find models that minimize the number of variables set to true. That is, I'm trying to get rid of as many positive features as possible. We know how to do that. You go ahead and assign values to leaves. Remember, now positive literals start getting the number 1 and negative literals get 0. And this is a boundary case of infinity. That's what I is. And again, I add up at and, I minimize at or. Now, what does this number 1 tell me? This number tells me that, look, this circuit is over 2 variables. In principle, there is 4 different instantiations that can satisfy this. And as you know, you have you have U and S. They could be both true, true, false, false, true, false, false. And this is telling you there is no model that has cardinality 0. That is, there is no model in which both U and S are false. But there are models in which precisely one of these guys is true and the other is false. And then you say, okay, get me these guys. Get me the minimum cardinality models of this formula. And we know how to do this. We go ahead and kill the edges that have children that with cardinality greater than the OR node, and those all will be killed. And the whole part of the circuit is no longer used, so you're only left with this. And this is now the minimized circuit. And it turns out that this only has one model, which is this. So the minimum cardinality models that satisfy this are just exactly one, where U is false and scanning is positive. I go and append this, and now I've got my explanation. So even though this was a positive instance, urine is positive, blood is negative, scanning is positive, and this guy's telling you, actually, you did not need urine to be positive. You would have made the same decision if urine was negative, blood was negative, but you need scanning to be positive, all right? This was a simple example in which there was only one explanation. It's possible that the minimized circuit has multiple models, and these would correspond to multiple minimum cardinality explanations, all right? So the point is, you are trying to find what is the culprit behind the decision. All right. You made a decision on an instance, but some of its characteristics were not essential for that. All right. And this is the best example in this case. And you're saying, why did you really make that decision? What is it about that particular instance that caused you to make that particular decision? And the point is, if your classifier is represented as a tractable circuit, then you can answer this particular question easily. And of course, this requires that you obtain that symbolic representation of the classifier. And as we mentioned, that happens through a compilation process that we will talk about next time. Now, this was oriented towards classifiers in which the features are positive and negative. And in a sense, it is easy to justify it when the classifier is monotone. We're going to take our break now. And when we come back, we're going to talk about the other type of explanation, which is more general, and that is PI explanations. And we'll see that this relates to prime implicants that we discussed last time. All right, so let's take our 10-minute break and resume our discussion at 11. Thank you.